Okay, hi guys. Welcome. Thanks for coming to our first event in the Alpha Rokai Scopus Colonies virtual workshop series. We're going to be having other workshops like this throughout the semester, so be on the lookout for that. We're doing things in like different tutorials and also like networking and portfolios. And we're also doing a stress relief workshop. So that's much needed probably right now. So yeah, you should just look out for more email correspondence from us. And also you can follow our Instagram, APX Scopus. You can get more information from us there. So yeah, so this was highly requested by our members. So we're really excited that we get to share it with you guys and get our organization more involved in the school. And also this is being recorded, so we're gonna post it on our YouTube channel. So we'll send out the link and also the file that you guys will make at the end for people who couldn't make it so that they can reference it. Okay, sorry, lots of like intro stuff. So this is like supposed to be interactive. So if you guys have any questions, feel free to like jump in or just like send a chat or something. Right. So, and then we're also going to be focusing on Grasshopper today because that was the most requested software tutorial. So hopefully this is helpful. And leading this workshop are our software experts that we're so excited to have help. First, we have JJ Bonetzi, and then we also have Tim Timilonis. JJ is a recent graduate of Kent State, CAED, now working at Bowen and Associates in Cleveland, Ohio as an architecture designer. And JJ had the opportunity to learn Grasshopper in his education at Kent and continues to practice with the software working at Bowen and Associates. So we're really happy to have him. And Tim is a fifth-year student at Syracuse School of Architecture, and he's a brother of the Syracuse Scopus Colony. And he's worked with Grasshopper for competition submissions and for work within the professional practice. So with that, I'm going to turn it over to them and stop talking. I'll make you the host, JJ.
Actually, could you make me the host first?
Right.
And then I'll transfer it.
Nobody has any like questions or concerns or comments before we start? Okay, perfect.
All right. Thank you, Gio.
No problem.
So as Gio said, today we will be discussing Grasshopper. And this is, of course, presented by Alpha Rokai Scopus Colony by myself and JJ Bonezzi. I want to reiterate, thanks everyone for coming. I'm really impressed by the turnout today and excited to really get to teach some people my understanding of Grasshopper. So to start, I'd like to talk about what is Grasshopper. It's basically a visual-based coding language where rather than using like Java or Python or something, this is actually visually based where you have different components and plugins that come in as different visual inputs and then model in live time in Rhino. With Rhino 6, Grasshopper comes pre-installed, so if you'd like to follow along with us today, all you have to do is type Grasshopper into the command if you have Rhino 6 or have installed the program, and it should pop up so that you can follow along. And so basically the basis idea for Grasshopper is to create and analyze models through algorithm and mathematics. So using applied mathematics in different algorithms to result in and produce designs. And this was developed in 2007 by McNeil and has been 13 years of development. So it's a pretty complex and sophisticated program. And hopefully we can start to introduce you to some of that today. So there are many different uses, and we'd really spend all day today talking about all of them. But some of the big ones that you'll see used in practice frequently is parametric and algorithmic modeling, of course. data-driven climate and site analysis, structural and form analysis, data manipulation, CNC fabrication, and unique physics-based design solution, such as tensile structures. And again, there's so many more different examples of how you can use and apply Grasshopper, but this is just kind of a short list of some of the big ones that you'll see frequently. And then you can look through these images here, and this is the tower in the top left is starting to use Grasshopper as a way to analyze climate and solar impact on a twisted facade in the city. And then the one just to the right is then a single surface manipulated into a three-dimensional object. And then down bottom left is you can start to use it within CNC fabrication, or on the bottom right, structural analysis visually represented through like this complex structure, using different points and nodes to model actual load, and then creating a visual representation of that. And so to do a lot of these things, you'll need Grasshopper, of course, but then within Grasshopper, there's a series of different plugins. Again, there's so many different plugins. We spend all day just talking about that. All of this is free, thankfully, on Food for Rhino, which is a McNeil sponsored site. But here you can begin to see kind of how you can apply these different plugins as a network that work with one another to create design solutions. Honeybee, as seen in the center on the left, is one of the kind of primary or most popular of these plugins that brings together a different network of other softwares to pull together a single design solution based on climate and site analysis. And so here you have the basic canvas for Grasshopper, and this is what we'll be working with today. And you can start to see the different components that will be input into the program and how they start to connect to one another in reference and feedback with each other. So here, one thing that I'd like to point out is this idea of moving from a single point on the first component down through, and you start to develop form from there. So it's very much a program where you build from the base level and then develop a more and more complex system from there. But I'd also like to point out that a lot of these components that you see here are things that you may be familiar with already from using Rhino, such as the point, polygon, divide, and rotate commands. They all function similarly to that of Rhino. The difference here is that it's a continuous feedback into itself, where you can adjust different components at different points in the design process to create a more seamless design where you no longer have to go back and redo things, but rather just change a slider. And here I start to begin to explain this more thoroughly, where you start with the point on the top left, and then you multiply that going down to the bottom left, then 2 points, and you offset in the X direction 30 units, and so you develop 2 points from there. And I should have mentioned, sorry, on the top left, you see it has the X, Y, and Z component, so you're placing a point within a field. Without any additional input, it's going to assume that it's 0, 0, 0, and so you'll start at the origin. And then you move and you place another point with an X component and move it so many units in that direction. And then from there, you develop that into a line, into a surface, and then into a solid cube. And with that, so once you plug in the X, Y, and Z coordinates, you get this cube, and you can begin to then manipulate these different
Oh no.
An extraordinarily simple explanation and example, but hopefully that begins to shed some light on what we'll be doing today. And with that, I'd like to hand it over to JJ, who will be leading the workshop today. If you have any questions, feel free, like Gio said, to speak up or put it in the chat. JJ will be leading this, and hopefully I'll be there to answer any questions that you have. So anyway, with that, good luck, JJ.
Well, I guess I have to talk now, which is good because I don't talk at work. So as Gio introduced me, my name is JJ, or formerly Jonathan Benezzi. Recently graduated, as we said. So somehow I found a job in this market, and I hope the best for all of you fifth years, the same opportunities to find something when the world decides to get back to normal. So let me go ahead and share my screen, and then we will get started. Okay, I have no clue what you're seeing right now. Are you guys seeing a spinning tower? Does someone nod? Okay, good. So hopefully we'll get through most of this today. We're going to try to keep it to an hour to an hour and a half, depending on how quickly we can go. And there's a couple of things, as Tim touched on, that I want to start with, which is that the principles of Grasshopper aren't just meant as a design tool. And this is something I found just only in my short weeks of employment, which is that understanding the underlying logics of how systems operate can really start to help you understand and reevaluate an approach to a design problem. So for example, there's a lot of qualities that we don't quite associate with when we design, right? An understanding of how we move objects through space, the understanding of the vectors associated with space, the reality is that the underlying logics of a line aren't just that there's a line, but that that line has an underlying direction and a start and an end. You don't really ever see those underlying mathematical principles when you're designing, but Grasshopper can really start to, in a negative way, expose those inconsistencies with lines, and the underlying mathematical logic. So it can be very frustrating. I'm just giving a brief overview of my trials and tribulations through the years, which is that it's very frustrating because you don't ever know why something is happening. And so my goal today is not to just show you what to do, but to try to explain what these components are, why they're doing what they're doing, and how they're operating. And if you can understand those underlying qualities and functions of those nodes, then you can start to really design and manipulate data. And data is ultimately just the underlying thing that governs representation of design. So long-winded nonsense for some food for thought. So for those of you that have Rhino, we're going to start with a totally blank canvas. One of the most important things that it can always throw you off when you start with Grasshopper is making sure that your units are correct. Some people start in millimeters. I have reprogrammed mine so that it starts in feet and then feet in inches, and I usually try to keep it to a 1/16 of an inch. Because, let me see how this is gonna work. So if I have this here, and I put this here, mine might take a second, there we go. Can you guys see both of these? Yes? Okay, cool.
Yes.
Like Tim said, Grasshopper doesn't really understand inches or feet, it just understands units. So it's really important that before you start working in Grasshopper that you know what your units are in Rhino, because you might be thinking, well, I need to make mullions. And mullions are usually done in units of inches. And so if you're using, say, like a number slider, you can just type a number. So like if I need 10, this is going to represent 10 feet or 10 of whatever unit you're working in. So that's one of the things to immediately acknowledge. Just making sure that there's a continuum between Grasshopper and Rhino. So let's get started. Let me pull up, and something you guys can't see, my cheat sheet. So we're going to start off with, as Tim said, the most basic thing, which is a point. And this point is actually for referencing. So I'll explain these tabs really quick. So you have the parameters tab, which allows you to reference in geometry from Rhino. So say I had a point in Rhino and I wanted to reference it, I could use these geometry nodes. There's other input nodes and things like that. And then it just kind of builds its way up. So at our most fundamental level, we have math and numbers. Numbers create sets or lists of data. Lists of data, when combined, can create points and vectors. When we combine points and vectors, we get curves and so forth. We get surfaces and I'm being haunted. So the first thing we're going to type is construct. I believe it's construct point. I always find this. If not, it's under vector point, construct point. Maybe it's CT point. I forget that one. Oh well. And this is going to start with a centralized node at 0, 0, 0. Obviously, if we wanted to move this, we could put other inputs in to X, Y, and Z and move it, but we're just going to keep it at the origin. And so the first step is trying to get a form for this tower. So we're going to start actually with a polygon. And a polygon can be any object. So, you know, in this case, we're going to use triangles. So we're going to set the number of segments on the polygon to 3. When you type, another side note, when you type a number in here, if you double click, that's how I'm doing this so fast. If you type 3, you're going to get what's called a rational slider. So it goes 3, 4, 5, 6, 7, 8, 9. You can double click on this and that will open up all of its properties. You can change it to, you know, an even, so it only does evens and odds. This does, you know, any variable of real numbers, etc. So we're going to use 3 as our segment. Radius, we're going to start with, typical tower is going to be about 100 feet in radius. Like that. And our centralized point is, this initial point is our plane. And that gives us just a base shape. I lost my train of thought. And something I always say is that you want to build in complexity, right? So you never want to have to go back and add and take away complexity. So just when I'm going to touch on that in about 2 more steps. But the first thing that we want to do is we want to fill at these corners, because these corners aren't really that sexy and it's not a really nice tower. So using, why is this going all the way down? There we go. So I just typed in 60. Obviously it should be more around 20, but that's the joy of Grasshopper, is that we can just kind of dial in whatever we want. So where I say moving complexity in is if we need to move this to the top of the building, right? So we have the ground plane and we need the roof plane. You never have to copy anything in Grasshopper. And this is why, because if this is how you grab from one and you push to the other. It's pretty intuitive. As you see, it always leaves residue, right? So like this node is the resultant of this function. This is the original function. So in essence, it's like, you never have to copy anything because it's always just inside of another node. But when we move this up, right, we could easily just say, I want to move 200 feet up, right? And that would be we have to tell it which direction we want to go. So if you just type Z, you'll get unit Z. So that way we can tell it that we need to go in the Z direction. So we could easily just move this curve up 200 feet. JJ, they don't know what they are. That's true. Do you guys see the names? No, I just occurred to that. Someone texted me. Up here in display are the options for how you display nodes. So yours probably looks like this, which I think is awful. So if you go to display and then do draw full names, you can read everything. This is how I like to work. It's much better.
I have a quick question, JJ.
Yeah.
For my number sliders, at least, when mine is going by like 0.025, it's not going by like integers.
So when you type it in, are you doing 2.0?
Well, like it's just like I'm only typing in the whole number, but it's just bringing it up as like for example, my like bottom number, or like the 14 is 14.000.
Interesting. So if you double click that and you change it from, it probably says R instead of N being integer numbers.
Oh, okay. Okay.
Yeah.
Oh yeah. Okay, that's it. Thanks.
Perfect. So as a, but something we could just move it up 200 feet, but we can build more logic into this. So let's say like So let's say hypothetically, we're gonna have to change this a lot for a client. So we're always gonna work on architecture in a floor-to-floor height, roughly 11 feet. And we can name this, which is always nice. I like to name stuff. That way you know what these sliders are doing when you have like 20 of them floating around. And then we can just multiply that using a multiplication node. Very, straightforward. And we can think about, well, we can afford to build 90 floors. Just like that. And these are my floors. So now what we've instantly done, which is when the whole script is done, we've allowed the ability to just simply come back and say, well, we can't afford 90 floors, we can afford 70. And we don't have to do the math to figure out all the other resultants. It's just very easy to just be like 70. So thinking of ways to break down your data even before you start putting it in is a great way to start like adding more and more complexity into the system. So if we were to say loft these two curves together, that would be a very boring tower. It would just be extruded. So we're going to rotate, and there's a few options. There's a lot of different rotation nodes. We're just going to use the generic rotate node. And we're going to rotate this curve that's in green that we moved vertically. And we're going to rotate it by some angle. I'm going to just type 60 for now. And what we'll notice is that if I'm turning this, it's moving very quickly, which is not what we'd expect from degrees of rotation. So what actually has happened is that there's hidden qualities inside of this node. And if you hover over angle and you right click, you can choose to do degrees. Or in this case, it goes back to radians for people that remember high school. So now we're rotating this by values of degrees, which is to me much more intuitive. But as you see, we get residue that's kind of like laying itself on top of each other. So to hide nodes, you can click a node and then you press these. What is it? They changed it. It's Control Space Bar if you have a PC. And then these guys are show and hide. I invert hide and show. And this is enable and disable. So we're just going to hide this for now. We don't need to disable the node. And then to get our, the last thing we want to do is that maybe we want this tower to taper a little bit as we go to the top, right? So you kind of get this twisting volume that kind of shortens itself, and then you get this nice long perspectival view. And to do that, we're just going to scale this geometry. And in order to scale this geometry, we need to know the plane on which we are going to scale, right? So normally, if we were designing Rhino, we just click in the center and scale it. But we need to kind of find that plane of reference. And so one way that we can obtain that is we actually can use what's called the area command. And if we plug this geometry into it, we'll get the area, which we don't really care about. But what's more important is we get the centroid of this piece of geometry. So we can take this centroid and use it as the center. Am I going too fast? Please someone tell me, because I'm just very...
People are saying in the chat that you're moving a little fast. I don't know if anyone needs anything repeated. They could speak up.
JJ, would you mind changing your view settings to full name so that when people are behind, they can at least see the yep, that's it. Thank you.
It is on.
Oh, because for mine, I actually have the exact command name for each command.
Does it look like
Oh,
this?
there it is. Yep, thank you.
Sorry, I have the icons on. So you can also turn the icons on or off. Is this more helpful? Okay, cool. I'm sorry.
You're doing great.
So now what we do is by using this kind of series of nodes is if we start to play with this stuff, right, is that everything moves with itself. So nothing gets lost, nothing as we change, you know, we can rotate, we can do all this kind of fun stuff. Literally one more node and we'll be at a happy place. So where was I saying? Scaling the top curve so that the tower tapers slightly. Yes. So we need to scale it by a factor, which needs to be a percent. And we get percents by dividing by 100. So we can just type, you know, say I want to scale by 62%. So we need to take 62 and we need to divide it by, come here, there we go. Divide it by 100. And ta-da. Now we are scaling this by a percentage. I don't want to see that. So, ta-da, we can just loft it as we would in Rhino. We can loft these two curves. Where? Oh, so we need to loft this curve, which is this green one, and we need to loft this original curve down here. You can actually plug two wires into the same node. All you do is when you're dragging this wire into the other node, you hold shift on a PC. I don't know what that is in Mac, so I'm sorry, but it's shift. And so that's how we can plug two things into the same node, and voila, now we have a shape. So I'm going to pause to make sure that everyone has a shape, and also because it's really fun to just kind of play around with the shape. Kind of get it dialed in to where you want it to be or what you want your shape to look like. You know, everyone can have a happy little shape.
AJ,
Yes.
now that this is done, would you be able to just like really briefly kind of like recap what we just went through? Like just like super briefly,
Yes.
just because I know I was like trying to pay attention, but also trying to type things in. So I think I might have missed it.
I'm sorry, that's my fault. So I'm going to go through this again. So we started with a base point of reference. So we constructed a point. Off of that point, we built the initial shape of our tower, which is with this polygon node. And we're controlling the polygon with three variables. One is how the radius of it, right? So if I want this to be more like way bigger, right? So the radius of the tower, we can control how many sides it has, right? Maybe we want to make that'd be a terrible looking building. And then lastly is if we're going to round the corners or not, if we're going to have a very sharp tower or if we're going to have a nice rounded corner tower. Next, we take that node or we take that initial curve and we move it up a certain distance. And we calculate that distance off of two things. We take a floor to floor height, which is 11 feet. Maybe it's 13 feet, maybe it's 16 feet, etc. And we multiply it by how many floors we're going to want in the building. And we're moving it in the Z direction. I could move this in the Y direction, but that's not going to give us a tower. And that gives us our second curve, which I hid, which is right here. The next step was that we knew that we wanted to kind of have this twisting form. So we rotated this top curve by a certain number of degrees, which is this node here, rotate and the 34. And then the last thing we knew is we wanted to taper the tower. So to do that, we had to scale that top curve down. But before we could scale it, we had to know the plane of reference of where we're scaling from. So to do that, we use this area command to get the center of that curve. And we use that as the center node or factor here. And then we just plugged in the corresponding geometry to geometry, the center to the center. And our factor is just a simple division of 61 by 100 to get 61%. And then we plug that final curve in with our initial curve up here, which is the bottom, and we get the lofted shape. Ta-da! Super fun. So the next thing we're going to need to build is floor plates.
JJ, before you go on, would you mind zooming out so we could see the entire yep.
So this might be tricky because as you zoom out, it will you know, it ghosts itself.
Right. That
So
actually works very well, but thank you.
Cool. So the next thing we're going to do, I'm going to talk about it first and then maybe do it slowly. This is going to be, it's like a trial. Like we learn each time we do a section how to teach better, iterating. So we're going to need floor plates in this building. And this is where, you know, this might be all simple and dandy to do in Rhino, but this is where Grasshopper really starts getting powerful because stuff will start compounding, right? You need to have 90 floor plates. And then eventually each of those floor plates is going to need to have mullions. Those mullions are going to be about 5 feet apart. So there's going to be almost 200 mullions on every floor with 90 floors. So God knows how many pieces of glass. I think that's like 17,000. So it really starts to build. And that's kind of where the complexity kind of builds itself in. So let's think how we do this in Rhino, and then we'll build it in Grasshopper. So if we were to put floor plates in this form, probably what most of us would do is we'd put either like a bounding box around it or something, and we would just contour the shape, right? And as we contour the shape, we're going to get closed curves, and we can close those curves, and that would give us planes to make floor plates off of, right? So we can take that same logic and bring it into Grasshopper. So the first thing we need to do is, well, we need the bottom to the top, right? We need to know that distance of what is from down here where this point is to this point up here. So we can do that in, there's a lot of ways you could do it. The simplest is to actually just use the command we used earlier, the area command. And we can find the center of this bottom curve from the polygon. And we can use the center of this one. I need a copy of that. We can use the center of this one here. So now we have the top point and we have the bottom point. And between those 2 points, we can construct a line. Use this line. This is the reference line. This is actually making a line. And you'll get start and end point, and we can put the bottom as the start, and we can use the top one as bottom as the start, and the top one as the end, and now we have the line. That is between the two. And then we can take this line, and now we just have to divide it by how many floors we have. So it's called, they changed the name of it a year and a half ago. Tim and I actually talked about this because I used an old one.
Divide curve.
Thank you, Tim.
Yes.
So you can use the divide curve node, which does practically what we think it would be doing. And so we can take this line as the curve. And all the way back here, we know how many floors we have. Right now it's 70. So we're going to pull the same guy over here to count. And now we've divided this into 70 segments, right? But as I said, if we go back and we start changing stuff, it's completely parametric, right? So now we have 80 floors, now we have 50 floors, etc. So once we have those points, we just need to find the intersection between the plane of reference at each point and the outside form that we've made. So Grasshopper is a little bit different because you can't actually contour anything. You have to think of things in the most basic of principles. And so what we could actually think of is making a plane, which is plane origin. And so what this is going to do is if we tie each of these points into the base here and as the origin, we'll see that we get a little plane at each of the points along this entire curve. I'm going to skip. Oh, 1 second. Sorry, I'm thinking about something. I don't want to confuse you guys, although I've probably already done that. So I'm gonna do this and then we'll work backwards. The command, so anything that's like not a flat surface, but anything that makes a volume in Grasshopper is called a brep. So the command is brep plane. If you just type those two together, It's this guy. And it's a node that solves the intersections between planes and breadths. You can't quite use, right? If we made a surface acts differently than a plane does. A plane is just a point of reference of data. If we actually started using surfaces have inherent directions built inside of them, so it can be kind of messy if we thought of like intersecting a surface with another surface. So that's why we use planes and surfaces, because it, it's much cleaner in that sense. If that makes sense, might not. But then we just thought, it's very intuitive, right? So plane goes to plane, and the breadth is this shape that we made earlier. And we'll get all these lovely intersections. So now we have to think about, okay, what's the next level of complexity, right? Floor plates have thicknesses. So how do we start to construct something with thickness? And what the hell did I do here? One second, I'm trying to read what I did. Even your own work sometimes is, why did oh, I know why I did that. Okay, we'll come back to that. Sorry, it's something later on that informs something. So slabs have thickness, so we can think of that, okay, we need to find a whole nother set of curves, right? So there's a top part of the curve, because these aren't just straight extrusions anymore. The tower is twisting, and so we would normally have to like make a bunch of intersections for the top part of the surface, make a bunch of intersections for the bottom part of the surface, and then loft the edges together. But luckily we can do that parametrically. So we can simply just move these curves down by a certain distance. So in the Z direction, Z is our motion. And we want to move it downward. So we need to type in neg, which will produce negative values. And let's say we want the slab to be 2 feet, 2 feet thick. It's pretty standard. And for the geometry that we're going to move down, we're just going to move the planes. Here are our planes. So we moved our planes down by a little bit of a distance. And if we copy this with Alt, we're just going to plug in our new planes here. So now we have a nice top curve and we have a bottom curve. But you notice that we're getting an error. And that's actually because we've moved outside, right? This plane at the very bottom is outside of the jurisdiction of the surface that we're trying to find intersections between. So that's where we're getting an error. So this is what I like to call like base level of like doing stuff. But we're gonna do some cool stuff with data. So now I'm gonna go very slow. So inside, you can use panels. Panels will show you what's going on inside each of these functions, right? So if I plug this in here, we can see these are all of the different planes that it's producing, run as data. Grasshopper has this lovely tendency where we don't start at 1, we start at 0. So even though there are 80 items or 72 items in this list, the last number in our list here is 71 because we start at 0. So what's something that's wrong with this if we're thinking fundamentally? Well, this bottom one, we don't need to make a surface at the bottom here. And we don't really need to make a surface at the top because of a building is going to be, right, there's going to be a parapet at the top. So the roof line is going to be sunken down behind the top of the building anyway. So we don't really need this top one and we don't really need this bottom one. So we need to get rid of it. Otherwise it's going to start messing things up as we get more complex, right? Because we've already incurred errors. So what we need to do is we need to what's called call the list, or we're going to remove a certain piece of information from these lists. I'm going to organize this a little bit. There we go. So we'll come back to this stuff. So we have our plain origins here. So if we go up here to sets and we go to sequence, we have all these different tools for controlling data. And we're going to use this call index node. And basically what this is going to do is we're going to tell it a certain number. Let me pull this up so you guys can see. We're going to tell it a certain number associated with this piece of data, right? These all have numbers associated with them. And we're going to tell it, please get rid of that. And so in this case, the list is this, or is we're going to work with the planes, right? Because we only have to remove the plane that we don't want, and then the intersections will all follow suit. So we want to remove this bottom plane. So we're going to type pull plane into list, and the indice is 0. So we're going to remove the very first one from the list. And let me hide all this stuff. There we go. So we can just watch. So what we can see here is that here's the original list. It's all green. And now we've removed that bottom one from the list, which is very nice. Hide that. So now we have to get rid of this top one. So if we're thinking parametrically, this is fine and dandy because the start of the list, start to end, it always is going to start at 0. So we never have to worry about this 0 causing an error. But let's say we wanted to remove this one. Right now its association is number 72, but what if we make more floors? Suddenly that's going to give an error. So we have to know this number or this item in the list parametrically. We can't just decide, oh, we need to remove number 72. And so the way we go about that is by using the length of the list. So this will always return the how many pieces of data are inside of this node. So this is 71 right now, but if I change this to say 99, it's always going to match. And then we need to remove this top piece of information. And like I said, you would think, oh, so we need to remove number 99, right? That would be a very logical response. But the problem is, no matter what, the list starts at 0. So the last item in the list isn't actually number 99, it's number 98. So we can actually go about that easily by just using a subtraction. And we can just take whatever this number is as it changes and just subtract 1 from it. And we'll get our answer that we need. So that will remove the top one if we run it through another call index. So if we took another one of these and we used this list, we're just going to keep pushing the list forward. And we removed this number. As you saw, there goes the top one. Top one's gone now. So now we have, you know, a nice normal roof edge, which is pretty typical of a building from, say, 0 to 10 feet. But let's say as a design feature, like, oh, I want a really tall parapet space. You know, I want like 60 feet of parapet space, something like the Shard, where all that space at the top is just parapet glass. So we need to remove more of these floors. And there's a cool way to do that, which is actually what's called a series. So if we type series is a function that basically lets you create a series of numbers, right? So it kind of does what it implies that it does, but you can tell it where I want to start, and you can tell it by what count, right? Do we want to go by 1s? Do we want to go by 2s, or, you know, any sort of number, and then how many we need. So to start, we're going to start at the last number that we got here, which is the last one in the list. And we're going to count by a negative value. So we're going to type negative. Come here. right? Because we don't want to count up, we need to count down. And let's say we want to remove 4 floors of space at the top of this building. So what we get, if we use a panel, we can see what's going on. So we're seeing that we got numbers 98, 97, 96, and 95. And this was originally number 98. So now we have 4 more numbers. And if we just run these numbers into this list, now we see we took out numbers 98, 97, 96, and 95. So you can really start to like play around with the data like this, and you can remove whatever you need to remove from the data before you keep moving forward. Does that make sense? Kind of. I know it's whatever. Anyway, and so then we don't need these planes anymore. One way you can, if you run a new wire into a node, it will disconnect it. It will like override the thing. You can also, I had a seizure. You can also just right click it and then do disconnect, and that'll remove it as well. But we're going to use our new list of numbers as the plane geometry. And so if I turn these guys back on, you see we now have the intersections for the whole building without the bottoms and without these top floors. Hooray, we did it. Sorry, I'm kind of sarcastic. And then the last thing, which took, I have a funny story, but it's not really that relevant. There is no like sweep. Well, there is a sweep command, but there's a cool command in Grasshopper that I wish existed in Rhino, which is called ruled surface, which will basically make a surface between curves, but it doesn't have, it can be like literally any shape of curve and it'll do it, which is really what's so cool about it. And we just plug in the top one and the bottom one, and now we have a whole bunch of edge surfaces. And as we would in Rhino, we can just cap this, cap the holes. And ta-da, we now have 78 floor plates or something like that.
JJ, yeah, I was just going to recommend maybe we can pause for a moment and ask if anyone has any questions. I know we just went over some pretty intense stuff, so I'm sure someone has a question. And if you do, please speak up now.
JJ, how do you change the values in the panel?
In these guys?
The yellow panel. How do you change like 98? Because mine are like different.
Well, yours are going to be different based off of whatever, like I have 99 floors.
Okay, so it's like auto-generated.
Correct. So like these yellow panels will just show you what's going on inside.
Got it.
Yep. Because maybe we could do it. Yeah, so now we can really start. So like, again, we can still play with all these sliders from the original part, and just be careful. You can really quickly crash even the best computers. But yeah, kind of fun to watch how it.
So we have a question in the chat about what a BREP is. JJ, I don't know if you want to take that question.
So, how do I describe? A BREP can be compared to any sort of poly surface that in Rhino. So anything that's a collection of surfaces. A loft is actually, it might look like a single surface, but usually when we loft something in Rhino, you're going to get isocurve lines down the and the edges. So that means that underlying in that surface is actually, in that poly surface, excuse me, is 3 individual surfaces, which can be problematic. Like if you've ever tried texture mapping something and you get weird seams, it's probably because it's a poly surface and not like a surface. It's a little So it's an underlying logic, but a BREP is similar to a closed poly surface in that sense, or any sort of poly surface.
You can also, sorry.
No, you go, Tim.
You can also use BREPs to import different forms from Rhino into Grasshopper. Right now, we've been working mostly Grasshopper into Rhino, but you can use BREPs to, say, as JJ had mentioned, if you have that loft created in Rhino and you'd like to start from that point, you can then import it into Grasshopper using a BREP.
I promise then it only gets, well, wait. The next two are pretty easy. How I made this purple, by the way, is you can highlight different sections of stuff and you can group it, which is easy to move stuff around. It looks simple now, but when your code is like from this corner to this corner, it can be a little messy. So something keep in mind.
JJ,
So,
can I ask another question whenever you're done?
Before we move on, I love questions. It's easier to get through the groups of, like, as you can tell, it's very much like, okay, we made the floor plates. Now we go have a drink, and then we come back and we deal with the next problem.
No, I just have two of my little node things are red, and it happened kind of early on, and I think I think I connected them to the wrong things.
What names are red?
It's two of the. I have an area one and a loft one that are both red, and I think.
And the loft one.
Yeah, I think it's those two that are right, like at the beginning of the.
This one?
I actually. Maybe, yeah, I think that one, yeah.
If you fix the area, it might correct the loft then.
Yeah, I would just make sure that it's coming off of the centroid and not the area here.
No, so it's the loft and then, okay, maybe,
No,
I think I actually, just kidding, I think I have an extra thing.
Oh, okay.
Heather, if you want to send me a picture, I can try to
Okay,
help you.
thanks, Tim.
Yeah, of course.
So, what's next? I have to think. I also hate that I hide stuff. Yes, time to make some cool columns. So we're going to take this initial lofted surface that we have, and we're going to subdivide it into a series of basically little squares. And we're going to use the corners of those squares to make lines, and then we're just going to pipe those lines, and that's going to make columns. So stay tuned for more. So to do that, we're going to start with what's called a U count. I think. I never remember the names of some of these. Oh, I totally lied. It's called divide domain with the squared. The reason why it's squared is because we're working on a surface and not just a line. We could divide the domain of a line, but if we square it, we get a surface. So what this gets into some like pretty heavy understanding of underlying logics. So built within all surfaces in Rhino are what's called the U and the V, which are, oh, hi, Alan. Sorry, my dog just came by. Which are mathematical ways of representing surfaces in 3 dimensions. So normally we think of the world as having up, down, left, and right. But when you have surfaces curving in space, you can't just use up, down, left, and right to describe surfaces. In actuality, there's 9 dimensions to curvature space, but we don't need to get into that. All you need to know is that built within surfaces is a U, or usually it's a horizontal part of a surface, and a V, which is a vertical part of a surface. But vertical is a quote unquote term because the vertical part of, a vertical line out of this surface obviously is not straight. follows the curvature of the surface, but it's more or less up and down. Anyway, so to do this, we're going to pull from our original shape here, the loft, as the domain. And we're going to subdivide it equally into pieces. I'm going to do this at around 15. We can check to see if this becomes too much. And I'm going to show you what this makes. This node just purely produces the data. So this node is producing all of this lovely data that we're then going to use to subdivide the surface. So if we type in isotrim, this is going to use the data. So that's what the domain is that it's asking for. It's asking for basically instructions. So we're giving it the instructions and we're giving it the surface. And what we end up with is a neatly divided surface in all directions, 15 by 15. Pretty fun. And what we get out of this is roughly 225 surfaces. So 15 squared, 225. What we can then do with this is now we can use each of those little elements and we can deconstruct it down to its most basic elements. So if we use the deconstruct brep component, again, this gets into the fine line of like what really is a brep. Like these surfaces will work as breps, even though they're surfaces, it's touch and go. But this will break it down into basically a list of faces, a list of edges, and a list of vertices. We need to use the vertices. This is where we're all going to work really carefully together to not fuck this up, because this is where I always screw stuff up. So inside of each of these items, I'm going to make a panel so you can see this. And I need to make, don't do what I'm doing. I need to show you guys what's happening. Otherwise you know. Where is it? Tim, do you know where the tree display is?
Sorry, I've been trying to help Heather. One moment.
If you didn't know, yes, I need that. What? Oh, it's called data tree. No. Sorry. I never remember the names of these. Yeah, la la la. I need to know the name. Google's your
Is it, you're not looking for list item, are you?
no, I'm looking for it. It's like a visual representation of what's happening, and it'd be like super helpful to understand.
Yeah.
Because no one ever taught this to me, and when I finally understood this, Grasshopper made so much more sense. But if I don't find it, maybe it's, nope, damn it. A quick Google search will help us. Yes, but I need to see that. It looks like that. Oh, wait. No. Ah, shit. Draw an actual tree. I want to see the tree. I need to see that. I need to draw an actual tree. See, oh, this is the greatest thing you'll ever know. Side note, grasshopper3d.com is basically the giant forum of people asking each other questions on how stuff works. And almost always, if you want to find something, people post like the actual files. So like I've gone on here and been like, Grasshopper panelization something something something, and you can get it. See, I'm looking for this.
Tree
Okay.
statistics. I don't know if that's what you're looking for.
What is it?
Tree statistics?
No.
Yeah, I don't think it is, but that's all I could find.
You watch. I'll find it. This is how fast I can find it. What is this thing? Param viewer. We found it, everyone. Okay, this is what was so important. Draw tree. So let's understand what's happening. A little lesson in data management. So what these little dotted lines mean, I'm going to put this one down here. This is more important than anything else that we're doing. And we're going to put this one down here. The ISO, and I'll put the panel here. Let's talk about solid lines first. Solid lines mean that there is a single path that is written inside the data, right? So we can think of it as a, like, right, so in our computer, there's like desktop, and then there's something else, and then there's like a folder, and then there's something else, right? So we can think of it as just like base level. The folder name is 0, and inside of that folder is 200 and whatever files, right? That's what's inside these solid lines. That's very linear flow of data. What starts to happen when we have these dotted lines is we're actually, basically there's a lot of folders, if we can think of it that way, in here. So what's happening is, if we can see here, so see how there's like little subsections here? So there's 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. Each of these surfaces, right? That's the initial folder, right? So we have like the 0th surface, the first, the second, the third, and contained within each of those surfaces is the reference data of 0.1, 0.2, 0.3, and 0.4, if that makes sense. So this is what we call flattening data. So if I right click this and I flatten this, we're just going to get one giant list. If I graphed data, color. So it's going to go from like there, 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 and there. And it's going to do the same for 1. It's going to go 1, 2, 3, 4, and so forth.
Hey, what's up?
Mute your damn computer.
What? Oh, you guys can hear me? Oh.
Yeah.
Hey,
So-
Sean, would you be able to mute?
Hey guys, my bad.
Yeah.
I'm sorry. You can continue with the tutorial. My bad.
But so that's kind of like, and that's kind of what this tree is showing, which is that the data is coming in from a single point, but it's going out to each of these branches. So something to know. So what, understanding that underlying principle of like what this is doing versus what this is doing is kind of like a really key concept to flowing the data through these algorithms. Okay, the lecture is done. The aside of my lecture is done. What we're going to do is use list item. And we're going to take these lists. So there's all these lists. And we want to extract a certain value. So you saw that there was 0, 1, 2, 3. Yeah, 0, 1, 2, and 3 from each of those lists, which coordinates to each point. And we're going to basically extract each of those points so that we can make lines between whichever parts of the that we want. Ideally, it'd be diagonals because we're making a diagrid. So the first one we're going to need is number 0. So these are all the number zeros. I'm just going to copy this down a bunch. Then we need number 1. Number 1. Then we need number 2. We need number 3. Ta-da. And if we do lines again, our favorite thing, so simple. This is where you can just kind of like figure it out. I know that sounds like such an asshole thing of me to say, is just figure it out, but like, okay, 0 and number 2 makes, okay, we have lines going that way. Cool, that's what I want. And then between lines number 1 and number 3 are going that way. That's what I want. Cool. Ta-da. One diagrid from a whole building. Super cool. But does the whole like lecture on data make sense? I know I'm not going to get an answer, but I'm just going to ask it so that I feel better about myself. And then lastly, we could do any other shape, but it's really easy to make pipes in Rhino. I love making pipes. So we can just use these curves and we can give it a radius. What's a good column width? 1.25. Cool.
I have a question. I've been using pipes before for a few other parametric work. How can you, instead of making pipes that are round, is there a possibility of just making a bar that's square? So I've been trying to do that forever and I just couldn't figure out how to do it.
That's a whole nother, I have done that because there was a project where I was very insistent that they don't be pipes. What you actually have to do then is you have to basically write a code that takes whatever shape. You know, we could actually just reference a shape from Rhino. That'd probably be a lot easier than doing all the scripting part. Also, be wary of the fact that sometimes it's easier to just like draw the damn thing in Rhino and reference it than go through all the effort. Like, just saying. But you'd have to take that curve, you'd have to orient it perpendicularly to these curves, and then you'd basically have to extrude along the curve.
Oh, wow.
Yeah. So you have to like take a curve, orient it, and then extrude it. It's a few more steps. And by a few more steps, I mean like this much more, like that much more steps.
Okay.
But it's not super hard. It's just, pipes are good for teaching. And ta-da, we now have a structure. But wait, oh my God, the floor plates aren't intersecting my columns. What am I to do? This is a terrible thing. It's fundamentally because when you make corners out of curved surfaces, you get flat things, not curved things. So this is the part, remember earlier when I kind of stuttered and I, thought about what I was thinking about. So we're going to use this information that we just made for the columns, and we're going to use that to re-inform our floor plates again. So the reason why is, how did I do this? This is totally convoluted. So this is the distance. So if we think about it, if we look in plan, these columns are sitting perfectly in the middle of this surface. So what we need to do is we need to take this surface here and we need to offset it out a certain distance. So that way our floor plates are, encapsulating all of the column space, which is really quickly easy to do. We can just use the offset surface command. And we're going to offset our original loft, our favorite friend. And we're going to offset it some distance. We could just use, well, this is going to be parametric because, what if we change the width of the column? Say the structural engineer comes back and they need to be like 2 feet in radius. I could not imagine a 2-foot radius column, but whatever. So we can just do a quick little multiplication and we could say, well, we need to be at least 2 times as far away from however thick the columns are or whatever. And sometimes this will happen, this offset in instead of out. So you just type a little negative command and voila, the whole surface is offset out. And then we will use this instead of this in our little intersection commands here. So boop and boop. Ta-da, now our floor plates are touching the grid. So if I turn off this loft and I hide this guy, we should just see, what is that? What is that? Oh, that's the ISO surface. We should just see, really? Columns and floor plates. Totally parametric. Which is kind of cool. So I'm going to pause because I went through a lot, because I went on a tangent. It was a very useful tangent in my defense, but I did go on a tangent. So does anyone have any questions before I move on to the next part? Otherwise, we could also stop here because this is a very good place to stop. When did we start? Did we start at 6? I'm being a full-on professor and I don't even know what time it is. Anyone?
I have a general question about doing something for fully parametric. As you can see, you're sometimes like the intersection between the U and V lines don't exactly hit the floor plate, I think. I was wondering, like, for like other kind of roofing structure, sometimes they don't exactly match well with like the grid you set up before.
Yes.
So assuming like the floor plates is a grid, it's a vertical grid in a sense. I was wondering, like, is there any like advice you would give? Like, is there a way like not doing computer work, but rather just like planning things out? Would you recommend planning things out by hand on a grid paper or like any normal paper, and then applying that same logic to Grasshopper, or do you think that's futile?
That's partly futile, but I am going to comment on what you, the point is, which is, I'm going to give the sad reality of the truth, which is that most of the time, Grasshopper is used in the industry just to get renderings out the door. Because initially, like, trust me, like, to do Zaha's buildings and to do SOM's buildings, you're going to need Grasshopper. But this type of stuff really doesn't, you know, you can get cool renderings out of it really fast. Like I need, like, a little aside, I had to design a 10-foot story hotel in 2 days and render it and have a video ready for a client next week, right? So like, when you have to design, model, and render in about 3 days, you don't really kind of worry about this minutia, because at the end of the day, they're just paying for the picture to see, like, oh, I like the idea, let's go forward, I'm gonna pay $60 million, etc. When you actually get back to the office and you have to start really dealing with like this type of condition, right? This is not going to work at all. You can't just have this not be in line with the floor plate. You'd have to come up with a different way of approaching the problem. So the way I approach this problem of making these columns is a very simple one of just, you know, randomly, you know, not randomly, like generically dividing the surface into 15 by 15 blocks and going from there. If you wanted to actually do this right, you would have to kind of go through this level of detail of creating intersections with the surface, and then, you know, finding those points that exactly match up with where your floor plates are going to be. And it's just a lot more in-depth process. So a node like IsoTrim is very much a representational tool, because it just generically will divide the surfaces. This is also what you use a lot if you see the really cool like CNC milled panels that are like, you know, they're like subsections of stuff that like parametrically changes size. It's like the type of thing because this is like, you know, this is super detailed. When you get to this level of like dividing a surface down to a very specific number and then finding the intersections and calculating the points and then rebuilding all the geometry. So a lot of times you can get away with stuff like this. That there's a reason why when I had to make the script at work that actually would make the curtain wall, it was about like the size of what you're looking at on my screen, because it just takes that many nodes of like fine tuning geometry and little tiny numbers and making sure everything is exactly aligning and referencing off of each other to kind of do that type of thing. But that's a very good question, because I don't think people ever openly discuss the fact that there's two sides to Grasshopper. There's one that's incredibly detail oriented and incredibly useful in the industry, and the other side is very academic, and you can kind of fudge it and, you know, keep the design going. So yeah, I thought that was a good question. Sorry, I went on a rant. I don't know if that was useful. Oh my God, are there 16 questions in the chat? Well, do we want to stop here, or do we want to see one more part? I can show you what the rest of it looks like. So the other part is I make the mullions, and then I make the glass surfaces. So it's up to you guys if you want to see that or not. I already know it's 7:08, so I'm not going to keep you. I'll share the script, obviously, so you guys can play around with it and reverse engineer.
Yeah, maybe it's easier for now if I know someone posted in the chat they'd like to see and understand how you move from Rhino into Grasshopper with the BREP.
Yeah, let's do that. We can do that.
And then, yeah, that's a really quick exercise. So
let's do this. You guys can watch how fast I work. Give me 1 second. Oh, it didn't do what I wanted it to do. Yes, where? Sorry, I have 2 screens open, so stuff's probably hiding. There we go. So let's say we have this little box, and it's a kind of a cool box because, you know, it's a little bit, hello, come your edges. And it's not just like a normal box, like it's like a cool box, and like maybe it turns a little bit, and there we go. Here's my little box. And let's say we want to like reference this box in Grasshopper. Boop. And where's my little, this guy here? So if we just type brep, when you right click this, set one brep. See, that's me being overly efficient. Set one brep. It's come back to Rhino. It says brep to reference up here in the command line. We just click what we need to click. And now you see it's like kind of greenish red. And so it's referenced, and we can do whatever we want with it, right? So if we needed to rotate it, we could. Now we can rotate it. Like I said, though, it's rotating around. It doesn't know the axes. This is a good example of why we needed that center point, because all it knows is this is 0, 0, 0 fundamentally. So it's, you know, it's just rotating around the center right here, but that's kind of fun. But you can use this in a multitude of ways. You could take this type of surface and orient it to another surface. Does that answer the question of how that works? I'm also looking.
I'd also like to just put one more thing in. If you right-click on BREP, you also have the option to set multiple BREPs if you want to select more than one object in the Rhino space.
I'm also trying to find. No. 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 I'm not going to have time to go over it, but everyone should download and watch the YouTube tutorial on elk. It's a, oh, did it do it? Maybe it did it. That'd be super exciting if it did it. Elk is a simple plugin it's basically makes site models. So it references, like, this is built in, this is, where is this? It might be Cleveland. So this is a simple script that I have basically built in. I'm not gonna have the time to go over how I did all this. There's only 3 nodes really in the whole script, but the big thing is, if you write this down, OSM, right? Yes, OSM. This is called OpenStreetMap. And you can basically find anywhere you want in the world, say where I live here and work, and you can export this file, and it will take the bounds of whatever this looks like, and it brings it in as an SOM file here. And you can use all these different data nodes, and you can do stuff with it, like making curves, and I have this other plugin that lets you bake stuff with like 1 click, so you don't have to go through and bake. So if I do this, and turn it off, now you see here in my Layers tab, I have buildings, shorelines, waterways, roads, highways, amenities, all as closed curves. And it's a really good way to make site maps. There's also the way to do topography with this, which is also explained. It's a really quick, it's like a 13-minute YouTube tutorial. But it's like one of my trade secrets that I've now given to like 60 people. So use it to your knowledge.
Yeah, and with that, I'd just recommend that if you're really interested in getting familiar with Rhino and its capabilities, that you look at the different plugins available, and also then find tutorials. They're really easy to find typically on YouTube, or I know that the university gives us access to Linder as well, if you need any additional resources to help with that.
Does anyone, any like general questions? Those are always like usually more informative than a tutorial, like just answering stuff you might want to know.
Speaking of tutorials, do you and Tim have any YouTubers that you know who do really well tutorials?
Yeah.
Not specifically for me. I usually do it on a case by case, because there's so much that you can do with Grasshopper. I wouldn't expect one person to cover all of it.
Okay. But I just want to say, Jonathan and Tim, that you guys, I watched so many LinkedIn and a lot of YouTube. You guys have been very clear and really helpful.
Well, thank you. I try. I'm not the best teacher, but
yeah, the difficult part about YouTube is that you can't ask them to stop and answer questions. So
I know it's gonna sound like very boomer of me to say, but there is a Facebook group that I follow called Grasshopper Tutorials. And it links to like people's really good videos, and I found really cool stuff on here. You know, I know that's like very pastiche, but something to consider. It's another resource, I guess you could say. Well, thanks for listening to me talk. I hope you guys learned something, other than being probably overly confused. I was very confused. Yeah, the first time I did it, I remember a professor, he literally just yelled at us and said, "I don't know, you figure it out." And I was like, I did.
yeah, a lot of this is going to come with practice. Unfortunately, you really have to sit down with it and figure it out for yourself. There comes a point where watching other people do it just won't be enough. You have to kind of problem solve on your own.
But I promise it is so rewarding when it finally works.
Yes, it's a good feeling.
Anything else? Thanks for having me. It was very, it's a two-sided conversation, obviously, right? You're learning things from me, but I'm also learning how to, eventually I'd like to teach one day, maybe 5 years down the line, but it's always good practice.
Yeah, and JJ, thank you so much for coming. Very helpful.
Well, thank you.
Yeah, thank you so much, JJ. It was really great. And also a lot of people have been asking me, like, we do have the recording. I didn't lose the first half. So we're gonna I'll splice them together and put them on the YouTube channel. And we're gonna email that out to everyone along with this file for everyone to reference after this.
Yeah, not this file. Although I could give you, if you guys want, as a present, you guys, I'll just give this out. My the site script I have that does this for dealing with me today. So have fun with using that. So
For that though, you need to download Elk, right?
Yes. So you'd have to have the Elk plugin imported, but once you have that, it's nice to have a script that's already written and works. So.
Thank you so much, JJ. You were great.
Thanks for having me. Oh God, oh, that's my email.
Thanks to everyone who came also, who's not in the frat.
And those who are, of course. Thank you.
Yeah, thanks for those who stayed the whole time.
Yeah.
Yeah, did like a bunch of people like dip out?
Surprisingly, not really. I mean, it's late.
Tim and Gio, are we going to have another? Are you guys having another another Grasshopper workshop in the future?
We're not planning on it, but if there's a demand, we can.
Yeah.
If people really want one, they can just reach out to us and we can plan another one.
Even if we don't do like a public workshop, if there's a demand or a question for a specific thing, we can always post to our YouTube channel with tutorials.
True, yeah. It doesn't have to be like a whole Zoom event thing.
That'll be awesome. Thank you.
Yeah, no problem. Okay.
Okay, I'm gonna go.
Alrighty.
Okay.
Thank you so much,
Thank you
JJ.
so much, JJ.
Bye.
Enjoy your evening.